And then we now have the talk that is pre-recorded at the end of the session. Yeah, so you'll fire up the video, right? Okay.
Good morning, everyone. Today I'm gonna talk about our work, Batch Anonymous MAC Tokens from Lattice. This is a joint work with Sherman, Lucian, Harry, Yongjun, and Baocang. Today's talk will unfold in 4 key parts. We'll start by exploring the critical challenge in anonymous token systems today, particularly how content threats and metadata leakage undermine existing privacy tools. Next, I'll discuss formal security models of anonymous tokens. The core of this talk will review how we achieve post-quantum tokens with private metadata through 3 key innovations in proof composition and batch insurance. Finally, we'll benchmark our results against prior work and map future directions for lightweight privacy protocols. With content delivery networks or CDNs growing like crazy, control over what we see on the internet is getting more and more centralized. But here's the catch. While they are trying to stop bad stuff like DDoS attacks, they sometimes additionally block legit traffic from shared IP addresses. And if you are someone who cares about your privacy, using tools like TOR, VPN, or H2P, you'll probably face endless captures. These prove you are human tests end up discouraging privacy tools, exactly what we don't want. Responding to this, Privacy Pass introduced anonymous tokens, a lightweight and efficient alternative to traditional anonymous credentials, so one captcha gets a token and bypass future checks. Now let's walk through how anonymous tokens work. There are 2 main actors here, the client, like a user, and the issuer, like a service provider. The process happens in 2 phases. First, the token insurance phase. The client starts by requesting a token. Think of it like asking for a digital ticket. They use 2 things, the issuer's public key and optional public metadata. It might be something like an expiration date. The issuer then creates a pre-token called response. To do this, she uses her secret key SK, like a master password, a hidden metadata bit. This could secretly flag suspicious activities, and the same public metadata mule to keep things consistent. Now the token redemption phase. The client converts that pre-token into a final token to use it while logged in some website. The issuer, or the verifier holding a secret key, verifies the token by reading that hidden metadata bit. If the token is valid, the issuer can extract the private bit with her secret key. The optional public metadata makes things flexible. Service can add a content like time limits without breaking anonymity. Okay, what might be required for AT in captcha? The first is private metadata. When you complete a captcha challenge, you got tokens that a hidden bit of a private metadata. The secret bit tells the verifier about the challenge result without the challenge knowing. Keeping this bit hidden is super important. It helps spot potentially bad clients without their realizing, and it stops people from training automated captcha solvers. Still, the client can check if the tokens are valid on their own, like making sure they've made the issuer secret key for the hidden tag. And the batch feature is a win-win for issuer and the client. The clients can get multiple tokens at once, so they don't have to solve a captcha every time they visit a source. And the issuer can handle lots of requests efficiently, cutting down the overhead. While the Privacy Pass uses the discrete log assumption, which is not safe for quantum attacks. Years later, we got AT constructions with both private and public metadata based on DDH and parent-based assumptions, but they're still not quantum safe. Despite all this progress, no scheme has both quantum safety and efficient batch insurance, 2 key features of the original AT that are missing in many recent proposals. Given the current situation and how important the features are, we've come up with the BLAST, efficient batch insurance, lattice-based anonymous and secure tokens. BLAST is a key verification scheme that supports 2-round insurance, batch proofs, private metadata, and public metadata. Its security is based on a hash version of modular LWE assumption. Thanks to recent advances in lattice-based blind signatures, our anonymous tokens are super compact, just 432 bytes. And our batch proof doesn't add much to the running time or the proof size compared to the single insurance proofs. We got these benefits by combining VOPRF with zero-knowledge proofs. Alright, let's dive into the basic of anonymous tokens. We got 5 core algorithms here. We have setup, which is responsible for generating those important public metadata. We have setup, which is responsible for generating those important public parameters. KGM produces the secret and the public key pair, SK and PK. The token interaction has 3 steps. Client creates a query with public metadata mule. Later, the issuer signs it with secret key and embeds the private metadata bit inside. The client finalizes the token, giving us a tag and a token. If the interaction fails, we got perp. For a secure anonymous token system, we need to ensure 3 key properties. 1 more on fungibility, no forging extra tokens, unlinkability, issuer can't track token usage, and metadata privacy via hidden bit stays confidential. And the read bit algorithm lets the issuer safely retrieve bit while keeping user anonymous. Okay, let's start with the first security, unforgeability. This ensures that even a malicious user interacts with the token issuer L times, they can't produce L at 1 valid tokens. Formally, for any adversary A in this game, the adversary gets L token queries via the issue oracle, but to win they must output L at 1 distinct valid tokens. The game enforces 3 key checks. First, no duplicate tags. Second, all metadata bits must be valid. And finally, every token must pass the read bit verification. So our security requires that the advantage is negligible, meaning forging token is practically impossible. After the unforgeability, let's address a subtle question. How do we keep the hidden metadata bit truly secure? This brings us to metadata privacy. The security game gives the adversary 4 oracles. Issue oracle, return pre-token with arbitrary bits. Read bit, retrieve the bit except for a special challenge token with metadata mule star. Challenge oracle. This oracle embeds the secret bit into the challenge query, and valid allows the adversary check whether a given token is valid. The adversary's advantage measures how well they get bit star, so the requirement is that the advantage is negligible. Finally, with secrecy and unforgeability covered, unlinkability ensures the issuer can't connect a client's initial request to their final token. The security game lets the adversary observe L client sessions and try to link shuffle tokens to their origins. So the challenger randomly permutes the tokens, and the adversary must guess which token maps to which session. If their success probability is negligible, then 2 else. 2 because a issuer can embed 2 different private bits as a pure chance. Then we achieve unlinkability. This formalizes anonymity. Even a malicious issuer can't profile users. Now we're about to talk about the construction. A core component of AT is the VOPRF, Verifiable Oblivious PRF, where an issuer holds a secret key S, evaluates a pseudorandom function fsx obliviously on input X provided by a client. Verifiability assures that on input fsx is computed correctly without revealing S can be assured by the client. Okay, let me break down how this works in the construction. The issuer holds a secret key S and commits to it publicly using an LWE instance. T equals SA and E. Here A is a random matrix and E is a low norm arrow vector. The client has the input by sampling a short random vector and computing C equals AX at E2 and FX. And attaching a non-interactive zero-knowledge proof to show this computation was done correctly. For the oblivious evaluation, the issuer computes an LWE sample where H equals SC at E3 using her secret key S and provides a proof that H uses the same S committed in T. Then the client unblinds H using the inner product of Tx. So why this works? When we run the modular P1, the error term in blue vanish because they are small. Our construction builds upon two fundamental cryptographic properties. Oblivious PRF ensures unlinkability, even for repeated token requests by the same user. External observers cannot correlate these interactions. Verifiability guarantees one more unforgeability, this preventing adversary from forging new tokens even after obtaining multiple valid ones. Now a critical challenge remains. How do we securely embed the privacy of the private metadata B? There is a gap in many existing frameworks. We'll address this by introducing two secret vectors S0 and S1 shared between the issuer and the verifier. The protocol operates in four phases. Initialization, the issuer publishes the commitment T equals SA add E. And second, client request. The client generates a tag from tag space and constructs the query C equals AX add E2 add F tag. Note that we replace the VOPRF input by a random sample tag. And 3. Embedding the private metadata bit. The issuer computes H as the inner product as C, the noise term E3, and our key innovation as B and B, where B is the metadata bit 1 or 0, and SB is chosen based on the secret bit B. At last, the token finalization. The client derives the token using Tx. The correctness again hinges on the relationship V is close to SF tag at SBB. The PRF term SF tag ensures authenticity, and the metadata term SBB is securely masked by the LWE assumptions. Building on how we embed the private bit using secret vectors S0 and S1, let's now address the unforgeability of this construction. This has bit in the lattice structure, but we'll now see how an adversary might exploit this design. A malicious client A can reuse the same tag but request tokens with flipped private bit and obtain two outputs V and V prime. Then he computes V minus V prime. This is close to S bit minus S1 minus bit with the inner product of E. This difference leaks the structure information about the secret vectors S0 and S1. With such pairs, the adversary can flip metadata bits in existing tokens and forge new tokens by manipulating the bit-dependent term. So to eliminate this attack, we adopt BLNS23's method with two upgrades. First, we replace the fx with a hash function hash1 mapping to RQN, and we inject randomness via a hash g by rho equals hash g x e2. This deterministically binds the client's noise e2 to their input x. So we redefine C equals AX E2 plus hash1 with the input tag and row. So why this works? The collision resistance ensures each C is uniquely tied to the tag and row. The issuer enforces rejecting reused C values, blocks attempt to request multiple tokens for the same tag, and extracts S1 minus S0 via different analyses. The random oracle hash1 and hash g prevents predictability, so even identical tag use fresh C due to the unique row. Now we've ensured unforgeability. Let's turn to our second security goal, unlinkability. Specifically, we must prevent a malicious issuer from embedding unique secrets in bit-specific vectors S0 and S1 to track users. In the current protocol, issuer published T equals SA add E, binding their master secret S as before, and in token insurance, the client sends C equals AX add E2 and a hash of tag row, where row equals hash G of X and E2. However, a rogue issuer could replace S0 or S1 with arbitrary random vectors for each token and generate unique per user H values. This link tokens via hidden bit fingerprints, and it violates the unlinkability by letting the issuer correlate C, the client query, with V, the redeemed token. So the fix, we use dual vector commitment. We force the issuer to publicly commit to both secret vectors for B in 1 and 0. We force the issuer to publicly commit to both secret vectors for B equals 0 and 1. Then, prove during insurance that the bit-dependent S bit matches either S0 or S1 in the commitment. By anchoring S0 and S1 to public parameters, we eliminate the issuer's ability to inject tracking marks while preserving the metadata bit functionality. By combining the unforgeability and unlinkability mechanisms we have discussed, we arrive at our complete anonymous token scheme. As shown in this block, to ensure security for both client and issuer consistent with VOPRI protocols, we require that each party must provide zero-knowledge proof for their computations. In this way, we ensure client honesty, generate queries follow the protocol, issuer accountability, responses align with public commitments, end-to-end privacy, no leakage of X, S, or bit. This achieves a verifiable and privacy-preserving token system. A critical innovation in our construction addresses how the issuer provides correctness of H without leaking the private bit. Let me unpack this challenge and our solution. So the issuer must prove the correct computation of H equals the inner product of SC at E3 and the inner product of S bit with B. Second, the proper usage of committed secrets S from T and S bit from T0 or T1, and complete privacy of the bit B. The first two equations might be easy as they are simple linear relations and one can apply basic lattice techniques, so the technical barrier is directly proving bit's involvement would reveal its value, this violating privacy. So our solution is introduce a new vector. We introduce a 2-bit secret vector new here. The bit's position equals 1. For example, the vector new is 1, 0 for the bit 0, and all other positions equal 0. This enables an elegant selector, new T0 and T1 equals TB. This is mathematically equivalent to using T-bit directly. For the privacy, the proof only reveals T0 and T1 were used, but not how. By having the issuer proving the knowledge of new satisfying this relation, we can achieve all three requirements without ever exposing B. Let's now examine how our zero-knowledge proof elegantly scales to batch insurance of N tokens. This extension is crucial for practical development where efficiency matters. For each token I in batch size N, the issuer must prove the correct computation of each HI using committed keys, proper use of either S0 or S1 per token, complete confidentially all bit I values. The batch computation will generalize the single token cases to vectorize the evaluations. H vector equals H1 to H0, and the shared public commitments T equals SA at E, and the pre-token privacy bits bit 1 to bit N. Now introduce a binary vector with length N that algebraically combines all terms, preserves the exact 1 property per token. So this method provides efficiency. The vector form allows proving all N relations in one proof, and privacy. The bit vector has individual bit I, while enabling batch verification. And correctness. The quadratic constraints ensure each bit I is properly binary 1 or 0. Corresponding to S bit I matches all public commitments. And our protocol elegantly extends to support public metadata new through simple but powerful modifications. The hash expansion. We introduce a new hash function, hash3, mapping metadata to the lattice vector. This allows public metadata mule to influence tokens without compromising the security. So the modified computation like this, the issuer now computes H equals the inner product of S with C at #3 mule. Critically, the original proof pi1 still validates C's structure, preventing malicious clients from manipulating #3 mule. Now let's examine how our construction compares to state-of-the-art alternatives. Our key benchmark results like this. Our scheme achieved a token size 432 byte orders of magnitude smaller than Stark-based 40 kilobytes or credential-based 80 kilobytes, and unlike blind signatures, we support private metadata bits. These results deliver 3 breakthroughs: a first lattice-based AT with private metadata, practical batch insurance via compact proofs, and post-quantum security. Looking ahead, we are further optimizing proof size using new lattice techniques and expanding real-world applications for privacy-preserving service. That's it. Thanks a lot for your attention.
Very much. And I have to apologize that the video started so quickly that I didn't even manage to mention Yingfei's name. So, well, there's no possibility to ask questions. No, we don't have a back channel. If you have any questions about the talk, please send email to the speaker.